In this session, we discuss excess pressure on the curved surface of a liquid or inside the curved surface of a liquid. Now, if I take a liquid and its free surface is horizontal like this, then if I consider a molecule here, that molecule will be acted upon by surface tension from both sides. Now, as it is pulled from both sides, the surface tension is equal and opposite, that effect will be cancelled. Then, the pressure at this level, that is atmospheric pressure, and pressure at this particular point, just below the surface, also equal. So, pressure outside and pressure just inside will be the same. There is no excess pressure coming if it is horizontal. Now, if I take a liquid surface like this and liquid is inside, it is curved like this, then the molecule at this particular point will be having the surface tension acting like this. Tangent at that point on either side. So if I resolve this surface tension into two, I will be getting two horizontal components and also two vertical components. But these horizontal components will be cancelling each other as they are equal and opposite. But the vertical component which is coming in will be pulling that molecule downward. There is a pulling effect of forces coming downward. So pressure at this particular point, if I say P outside, then pressure inside will not be the same. It will be a little greater than the outside pressure. So inside the curved surface, there will be a pressure excess coming due to the surface tension action. And if you take a liquid column like this, liquid outside, and a point here, if I take same case, liquid is outside and here is air, then there will be a resultant effect inside the curving. So, if this curved surface has to balance, then there must be an excess pressure to come, an additional pressure to be coming inside the curved portion of the liquid. This is what we call excess pressure. Now, when the drops and bubbles are formed, there is curving of the surfaces coming, and therefore there will be an excess pressure inside the drops and bubbles possible. So, we have to discuss the excess pressure inside a liquid drop. Excess pressure inside a liquid drop. Now, when we consider a liquid drop, this liquid drop will be having liquid molecules inside. Inside will be having liquid molecules, okay? Liquid molecules present. Alright. Then, due to curving, pressure inside Pi, and if I consider pressure outside PO, according to this concept that Pi will be greater than PO, therefore Pi minus PO will come there, and this is equal to excess pressure inside. So due to curving, there will be pressure extra coming inside, and that is equal to this pressure. Now we have to derive an equation for this excess pressure, as this addition is coming due to the presence of surface tension. And surface tension is the reason for forming a drop in the form of a sphere. So to find that, what we consider here is, let us assume that the surface area is increased through a little bit. We assume that the surface area is increased through a little bit from all sides. Assume that the radius is r for the drop, and this excess is coming as delta r. So an amount of work is done and the surface is increased through delta r, suppose, and without change in the temperature of the system. Okay. Then we can find that work done in increasing the size of the drop as equal to force due to pressure Pi minus Pu into 4 pi r square. So this is the force due to the excess pressure acting outward into delta r. This is the work done by the excess pressure in expanding. Okay? But we have to, this is force. Each point on this drop, there will be a force of this much is coming, and that into delta r gives you the work done in expanding. So this is in terms of excess pressure, but somehow we have to relate this with the surface tension. So I take surface energy and work done in terms of surface energy is equal to surface energy into increase in surface area. This is according to surface energy. Now that will be equal to surface energy is equal to surface tension, so let the surface tension be T for the liquid. Then surface tension into increasing surface area, that is 4 pi r plus delta r the whole square. This is the surface area of the final drop minus 4 pi r square. So this is the increase in surface area, surface tension. So in this case, only one free surface is there. Therefore, surface tension is not multiplied by 2. Only one free surface, so single surface tension is to be considered. Now, if I expand this, I will be getting the equation, that is 4 pi r square and 4 pi r square goes. Then a 4 pi delta r the square will come. So expansion is coming like this: 4 pi r square plus 4 pi delta r the square plus 8 pi r delta r minus 4 pi r square. This is the expansion of the bracket. A plus b whole square form. So 4 pi r square and this 4 pi r square is cancelling each other. Then becomes 0. Then 4 pi delta r the square. Delta r being very, very small, the square of that becomes even smaller. Therefore, this part can be neglected being very very small compared to this function. So what remains here is only this much. Therefore, the work done will be equal to 8 pi r delta r into surface tension. So this is the work done in terms of surface tension and this is in terms of excess pressure. So both these two equations are one and same, therefore we can equate the two and get, by equating the two we get as we equate these two, we will be getting that Pi minus Po equal to Pi minus Po equal to 2T by R. Because 4 pi r square is here, delta r is coming here, delta r and delta r goes, then 4 pi and 2 will be coming there. So 2T by R remains there for the excess pressure inside. So the additional pressure is created by what we call the surface tension, and this quantity 2T by R is called surface tension pressure or pressure due to surface tension. Okay, so this is the extra pressure coming inside due to the curving of the liquid surface. Okay, understood?